Good evening. The last of our lectures in the gas laws unit will be covering the kinetic molecular theory. This is the postulates that we will use to explain the different properties and behaviors of gases. In this video, we will also talk about the law of effusion and how that will relate to the speed at which the gases will move through an opening. So up until this point, we've talked about a bunch of different gas laws. We've talked about the Boyle's law, Charles' law, Gay-Lussac's combined gas law, Avogadro's law, ideal gas law, and all of its derivations. And the laws are going to simply tell us what happens in nature. Each of the different gas laws that we've discussed tell us what we can observe under laboratory conditions, but it doesn't explain why. And that's what we're going to focus on today. Why are all these laws observed? We will discuss a theory, which if you remember is always just the explanation for what we see, where the laws just predict what will happen. So we're going to discuss a theory to help explain all of these different observations. So when we talk about pressure, the pressure that is inside of a container, again, is going to be coming from all the collisions with the gas molecules and the container walls. So we have to look at what is taking place with all those collisions to help explain what takes place. We will now describe the kinetic molecular theory postulates. These are going to be tenets that all ideal gases are going to follow under perfect conditions. Please remember that these will describe the ideal gas behavior, which under certain perfect conditions will occur. Now, an ideal gas, if you recall, is an imaginary gas. So when we're talking about all these things, this doesn't actually happen for all gases, and we'll talk about which ones are true and which ones are false. But if we had perfect conditions, these are how gases would act. So the first thing it says is that the gases consist of tiny particles, atoms, or molecules. These particles are going to be so small that compared with the distances between them, because remember, gases are made up mostly of empty space, that the individual atom's volume compared to the overall volume for the gases is going to be negligible. So again, mostly made up of empty space. The total volume for a gas will occupy about 1,000 times more volume than the same number of particles for a solid or a liquid. So you can think about that easily in terms of moles of water. So we know if we are talking about water vapor, H2O as a gas, 1 mole of that gas will equal 22.4 liters. If we look at water as a liquid, the density of water, if you remember, density of water is 1 gram per milliliter. So the molar mass of water is 18.02 grams per mole. So based on the density, you're talking about having 0.018 liters for the same volume of a liquid for 1 mole of water compared to the gas. So as you can see, about 1,000 times greater, a little bit more than that, for the volume of the water vapor compared to the water as a liquid. The second piece of the kinetic molecular theory states that the particles are going to be in constant random rapid motion. They're going to move in straight lines in all directions until they collide with something else, whether that something else is another particle or the container wall, doesn't matter. But these collisions that we are talking about, these are called an elastic collision. So that's just a vocabulary term for you. And basically, when we talk about an elastic collision, that just means that there is no net loss in energy. So basically, the particles, even though they're colliding with other things, there's no transfer of energy from one particle to another. The collisions with the container walls will cause the pressure that is exerted by the gas. The greater the number of collisions, more forceful the collisions, the greater the pressure will be. The next tenet that we have is that the particles are assumed to have no forces of attraction or repulsion between each other, and that allows them to just easily slide by one another without deviating from their path. And then finally, we know that the average kinetic energy of the gas particles is directly proportional to that Kelvin temperature. So when we are looking at that, you just have a very easy little saying to help you remember. Heat them up, speed them up. So we have a direct proportion. Temperature increases, the kinetic energy of the particles will increase as well. Now, as far as which ones of these are not true, so when we talk about the ideal gas behavior, we're going to compare it to real gases, what we actually see happening with all the gases in our environment, inside of the laboratory, so on and so forth. So when we talk about these, the ones that do not hold true are the particles are in constant rapid random motion. It's more the part about the elastic collisions. That is the untrue part. They are actually inelastic. There will be some transfer of energy between the particles, and we will see a loss of energy in some of them. And then the other one is big time, and that is that the particles are assumed to have no forces of attraction or repulsion. If this were the case, if no gases would ever have attraction or repulsion between those particles, then if that were the situation, we would never have any liquids on the Earth. So as soon as those substances were able to transform into the gas phase, they would never condense back down into a liquid. So you have forces of attraction or repulsion that will take place and allow for condensation and eventually, in the terms of like water, getting rainfall to occur. So we're going to focus on a few of the items from the kinetic molecular theory that do hold true. So when we talk about the meaning of temperature here, what do we actually see as we change the temperature for these gases? The Kelvin temperature, which hopefully you remember, is the temperature that's based on the motion of the particles. We talked about this before. The lowest temperature that we can get to is called absolute zero. And if you remember, hopefully, for absolute zero, that is when all motion stops. So when those particles come to rest completely, that would be at absolute zero. It is directly proportional. The Kelvin temperature is directly proportional to the average kinetic energies of the particles in a sample of matter. So again, that's your heat them up, speed them up concept. I could go through a long derivation where we look at the definitions of velocity and momentum, force, pressure, as it relates to the number of particles within a particular sample to come up with a direct relationship for us. But I'm going to give you the Cliff Notes version for that and just tell you that our relationship that we have is that the average kinetic energy for a sample of matter is equal to 3/2 times RT. The R again is that universal gas constant, which we had in kilopascals, which is the 8.314. And that's also what we'd use for energy, because the kinetic energy of the particles would be in joules. So you have this part right here, based on physics again, that would be a joule per mole Kelvin. So you can use that 8.314 as a unit for that, but again, that's all you need to know. I'm not going to ask you how to derive it or anything else. So just heat them up, speed them up, directly proportional, main feature of temperature. When we look at the relationships between pressure and temperature, the gas pressure that you have inside of a container that is sealed will increase as the temperature increases. Reason being, again, because as the temperature increases, the gas particles are going to be moving faster, i.e. they have a higher kinetic energy, and so as a result, they will undergo more frequent collisions. Those more frequent collisions would again build up the pressure until it reaches that maximum capacity and it would explode. When we talk about the relationship between volume and temperature, same topic concept. The volume of the gas will increase with temperature because the gas particles are speeding up. The containers are flexible instead of rigid, so as a result, to equalize the pressure both inside and outside, it's going to have the volume expand to lower the pressure on the inside back to whatever the outside pressure happens to be. So it's kind of using Boyle's law in a way to help relieve the extra pressure that would be created by having the more frequent collisions by expanding out. When I expand out, I have a larger distance between the particles and the container walls, so the number of collisions will drop. So when we're looking at the different assumptions, when we talk about the volumes here and how that affects the forces of attraction or repulsion between them, you can see very easily with this diagram on the left what is going to take place. When we are looking at the volume of the gaseous particles, on the left side, under that low pressure system, because the volume is so large, the particles are able to space out far apart from one another, and they have a much greater distance apart from each other. Hopefully you remember talking about that lovely Coulomb's law in our periodic trends unit, and so relating the force of attraction to the distance apart of the two objects. So by having the particles further apart, I have a lower force of attraction that is acting on them. So when we talk about the high pressure situations, now because it's a higher pressure, the volumes are going to be in a much smaller range, and so I have the gas particles that are going to be much closer together, and because they are much closer together, the force of attraction will increase greatly between them. That increase in the force of attraction between those gas molecules will cause deviations from that ideal behavior. So when we are looking at your ideal gases and versus your real gases, the deviation, one of those areas that will occur is when you have conditions of high pressure. So again, making the particles closer together. And also we can deal with it in terms of temperatures. So when we have these gases found at low temps, that will also cause the deviation to occur, because now there's not enough energy to overcome those forces of attraction, and eventually they will combine together and condense the liquid. So again, the high pressures, low temperatures, they will cause the deviation from the ideal behavior. Now, if we also look at the relationship with the forces of attraction that are taking place, if I have an ideal gas, you think about that just like playing pool at your house or at a restaurant or something. If you have the cue ball and you strike the balls that are on the table, they're going to transfer energy. We know that there's going to be a net loss of energy along the way. With the ideal gas, we assume that that's not going to take place, that you're going to have no net loss of kinetic energy. So as it strikes the walls of the container, as it strikes the other particles, it's just going to bounce off at the angle of reflection that it would normally do. However, when we look at real gases, now you can see that this one particle right here has forces of attraction with these three particles. And because these other three particles are pulling on it in the opposite direction from which it's moving, that means that the particle is going to strike with less force and also at a slower speed with the container wall. You can see that by the size of the arrows. And so as a result, this real gas would feel a lower pressure overall compared to the real gas or the ideal gas. So again, pressure being high, temperature being low causes the most deviation. When we talk about the types of particles, this is also where we can get into play with the different types of bonding that's taking place. So as far as your deviations, your nonpolar molecules and your diatomic elements or diatomic molecules, because they are perfectly nonpolar, they will exhibit the most ideal behavior. So I'm going to say acts most ideally. And then your greatest deviation is going to occur with polar molecules, will exhibit the greatest deviation. And again, the whole concept of those partial charges, we talked about dipoles being formed within the molecules. So again, in that situation, if I have those dipoles, that will be created within the molecules. They're going to have a stronger force of attraction for those other molecules, and that is going to cause the greater deviation. So we think back to that last illustration that we just saw. How would you expect the pressure of the gas to change if suddenly the intermolecular forces were repulsive rather than attractive? So as that particle was moving, if it was being repelled by those other particles, then what would take place? So take a moment, try to think about it. Would it increase, decrease, or would it not change? So take a moment, think about it. And hopefully when you put your answer down, you would choose A. And if you just simply think about it, that repulsive force as that particle moves by, it'd be kind of like giving it a shove in the back. So it's applying extra force in that direction, going away from the particle. And so as a result, it would increase the speed, increase the force of the collision, and so as a result, the pressure would also increase. So when we look at this next example, which gas deviates most from ideal behavior? I hate to tell you, this is where your Lewis structures are going to come back into play. So if I would take and draw these out really quickly, Cl2 would have this particular Lewis structure. And make sure I get all those electrons out in visible plain sight. Okay, so there would be Cl2. CO2, I would have this as the structure. NH3, we would have this as the structure. And then H2 would just be HH. So as we're looking at all of these different things, remember nonpolar gases, diatomics, they all will deviate the least amount, and polar compounds will deviate the most. One other thing too, the more massive the molecule is, i.e. the greater the molar mass, the greater the deviation is going to be as well. We'll talk about that in our next unit. But as I'm looking at this, because I have the Cl-Cl bond here, I know that this is a nonpolar molecule. When I look at the CO2, even though we have individual bond dipoles, if you remember, we're looking for symmetry. And I told you guys 3 little rules that you could use to determine the polarity. So if you recall, we said that if the central atom is bonded to the same element with no lone pair electrons on the central atom, then it would be nonpolar. If the central atom was bonded to the same elements but had lone pair electrons, then it was polar. And if it was bonded to different elements, the central atom is bonded to different elements, then it would be polar. So in this case, I have no lone pair electrons on the CO2, both of them oxygens, so therefore I know that this would also be a nonpolar molecule. When I look at the NH3, I do have the same bonds between nitrogen and hydrogen. However, because I do have that one set of lone pair electrons, I know that the ammonia would be a polar molecule. And then finally, H2, same way. It is a diatomic element, so therefore it will be nonpolar. So the greatest deviation would occur with the polar molecule, so my answer for this would be C. So we can use the KMT to explain a lot of different properties that we see. We have low density for gases, if you recall. Low density would be described based on the fact that the particles have so much empty space in between them. We know that gases are fluid, so they can slide by one another without those forces of attraction or repulsion greatly impacting them. We have the expansion property because they're moving in random directions at a constant, rapid, random motion, we know that they will expand to fill their containers. So when we start to look at a couple of processes, we have effusion and diffusion. Now, please notice the diffusion that we're talking about here with the gases is completely different than the diffusion that you do in biology when you're talking about crossing a cell membrane. There is no cell membrane involved in this. There's no area of high concentration and low concentration. You're just simply spreading randomly one substance throughout a space or a container. When we're talking about effusion, we're talking about the escape of a gas molecule through a tiny hole into an evacuated space. So just as a definition, that term evacuated space basically does mean that you have a vacuum. So there are no particles initially present. So we have no particles present in that chamber. So here's the big difference. Effusion, the rate at which a substance will effuse compared to the rate that it will diffuse, will always be greater. And that's because once it goes through that tiny little opening in the chamber, there's no other particles that are inside of that chamber to cause the molecules to veer in another direction. So they're going to go in the straight lines until they hit the container walls. Straightest line, shortest distance, greatest speed to cover. When we talk about diffusion, because it's just spreading from one thing to another, you can think about mom or dad making a cake or something. My daughter loves to bake, so she actually made some cakes today, and so as she was baking them, you could smell it all throughout the house. That's diffusion, the random mixing of those gas particles throughout the container, and you can smell them normally. So you've got that, but I want you to notice the picture here, because all those particles that are coming from the cake that my daughter was making are traveling through the house. There's already other gas particles that are there. And so you have collisions not only with the container walls, but you also have collisions that are occurring between the particles with the other air particles that are already present within the container. And so you have a lot more deviation that's taking place, a lot more change of directions, and so it takes longer for those substances to spread and mix entirely throughout the container. So effusion, we're escaping through a tiny opening. You can think about like a pop tire. If you run over a nail with your car, you have all the air escaping from the pressurized chamber inside of your tire to the outside air. And so that would be an example of effusion. You have the diffusion again, just the random mixing of the gases throughout a container. So we're going to now look at some of the math that's involved in calculating the rate of effusion. So when we describe the rate of effusion, we're going to talk about Graham's law. So for Graham's law, and again, this specifically relates to effusion in particular, but Graham's law will relate the molar mass of the two gases to their rate of speed of travel. So if we talk about rate of speed, that again is referencing a velocity. Now, we can set this up as either R's or also V's for the velocity. So I can say the rate velocity 1 equals rate of velocity 2. That is going to be equal to the square root of the molar masses of the two gases. Now, the lighter the gas is, the faster it's going to travel. I want to take a moment to explain why that is the case, and that will also explain why we have the inversion here, where we have R1 over R2 versus M2 over M1. So the first thing that we always do when we're talking about these different gases and comparing them, we need to make sure that they're having the change occur at the same conditions. So when we have the same temperature, based on our definitions, we know that at the same temperature, gas A will have the same kinetic energy as gas B. And from physical science or your physics class, we have an equation, kinetic energy equals 1/2 mv squared, with v being the velocity, not being volume. So just watch out for that, because again, it's lowercase v, not capital. So when we talk about the mass, this mass here, that will be the molar mass for our gases. So because my two gases have the same kinetic energy, I can set the two equations equal to each other. So I could say 1/2 the mass of A times the velocity of A squared equals 1/2 the mass of B times the velocity of B squared. Notice here my two 1/2s, they can also cancel off. So I have MA times VA squared equals MB times VB squared. So when I look at that, if I get the velocities on the same side, I get the molar masses on the same side, I can divide both of these by the VA squared, and that will give me, for my equation, MA equals MB times VB squared over VA squared. And then I can divide both sides by MB. And when I do that, that now gives me my velocities on one side, my molar masses on the other. So I'm going to continue right up here. So I'd have MA over MB equals the VB squared over VA squared. So the last thing, if I just want to get a ratio of the velocities and not a ratio of the velocities squared, I can take the square root of the entire side. So notice my A and my B are inverted in their places. So that gives me overall the square root of the molar mass of MB over B versus the molar mass of A, and that's equaling the velocity of A over the velocity of B. Either way you want to do it, doesn't really matter, but again, your velocity and your molar mass need to be inverted. So this is the equation that we would have for Graham's law. Now, as I said, there is a little bit of a difference in the calculating the speed of diffusion because of the fact that we are talking about the particles being able to collide with other particles and change directions as they are spreading. So there's a little bit difference in the calculation for it. We would use something we call the URMS, like the average velocity of those particles, to help us describe what is taking place with diffusion. Okay, so I wanted to take a moment to go through a couple different ways that we can look at Graham's law problems. So the first one just asks us to compute a ratio of the effusion of gaseous ammonia to gaseous hydrogen chloride. So when we're looking at this, anytime you have the ratio, they don't care what the actual velocities are. They just want to know the difference between the velocities, or that ratio of the velocities in comparison to each other. So you can choose whichever one you want to be your gas 1, gas 2. My own thing that I've noticed with my students over the years is that they really don't like working with decimals and fractions. So what I would recommend doing, because we know that we're going to set up in terms of the molar masses, I would set it up where I have the molar mass for my heavier gas on top, which in this case would be the HCl, and divide it by the lighter gas, the NH3. That way I know when I do my manipulation here, the volume, or the velocity, excuse me, for the NH3, because it is my smaller gas, would be quicker than the velocity for the HCl, because that would be my larger gas. And as a result, I'm going to have a number greater than 1. So that's just what I've seen over the years. If you don't mind that, go for it. But it just doesn't really make sense to say that something is 0.62 times faster than something else. It needs to be greater than 1 to make it faster. So that's my only argument with that. You wouldn't be wrong if you did the inversion on it. It just doesn't seem to make quite as much sense. So if we look at the molar masses, ammonia, if you remember, again, is NH3. Hydrogen chloride would be HCl. So as I'm looking at the square root of the molar masses, the molar mass of HCl, as we had said, putting that in the numerator, I would have 36.46 grams per mole. And for the NH3, I'd have 14.01 and 3 times 1.01. So I'd have 17.04 grams per mole. Notice my grams per mole cancel. So I have kind of a unitless number here for the velocities ratio. And 36.46 divided by 17.04, that would be 2.13. If I take the square root of 2.13, I end up with 1.46. So we can say that NH3 travels 1.46 times faster than HCl. Okay, so for our second problem, it says we need to find the molar mass of an unknown gas if 94 seconds are required for a given amount to escape from an effusion apparatus, but only 54 seconds are required for the same quantity of neon to escape under similar starting conditions. So key thing, I don't have any numbers other than the 94 and the 54, but I do know a substance, which is neon. So I can always tell the molar mass of neon from the periodic table. So that would be 20.18 grams per mole. The other aspect that I want you guys to think about, we have a equation for velocity. Velocity is equal to distance over time. So when we talk about this here, if it took another gas 94 seconds, that it took neon only 54 seconds to effuse under the same conditions, then just remember, longer the time for the same distance, smaller the velocity. So when I set up that equation, because the velocity of neon requires less time, I know that neon will be my faster gas. So I'm going to do the same type of thing, and I'm going to put the volume of the neon over the volume of my unknown. Now, to get this ratio to be set to see how much faster it is, I'm going to take the times here and invert them, because again, if I did time getting it out of the denominator, it would be in the numerator. So I'd have 94 divided by 54 to give me the ratio of how much faster the velocity of neon is. So if I do 94 divided by 54, that would give me 1.74 times faster. So now I can set that equal to the molar mass of the unknown substance divided by the molar mass of the neon, which is again 20.18. So 20.18 over the m for the unknown, get our monk here, and that would equal 1.74. So to solve, I'm going to take the square of both sides. So if I take 1.74 and I square it, that gives me 3.03. So I can now take that and multiply that value times the 20.18 grams per mole. And if I multiply that, I'm going to get approximately 61.15 grams per mole. So for our last example, we have an unknown gas diffusing 37.2 centimeters in the same time that it takes for ammonia to diffuse 83.9 centimeters. What is the molar mass of the unknown gas? So we can use that same type of concept, but in this case, we want to focus on the distance that is traveled and how it relates to the velocity. So if I'm dividing by the same amount of time for each of those gases, but the ammonia went 83.9 centimeters versus only 37.2 for the unknown, I know that the ammonia would be the faster gas. So I can use that same basic concept now, because the ammonia was determined to be faster. Again, we don't care what the actual number is for the velocity. We just need to know which one's faster. So I'm going to put that over the velocity of the unknown. And so I can set up my ratio of the distances, just like we talked about with the times. Because you can see right here, because I have distance divided by the same amount of time, that's the same thing as the velocity. So I could take now the 83.9, and I don't have to invert it this time because the distance is in the numerator. I have the 83.9 centimeters divided by the 37.2 centimeters. So if we do that real quick, 83.9 divided by 37.2, it traveled 2.25 times further. So we know that it's traveling at a rate 2.255, so we'll go 2.26 times faster than our unknown. So again, the NH3, 2.26 times faster than the unknown gas. So I can set that up and just simply say 2.26 equals the square root. And because the other gas is slower, I know it will be the heavier of the two. So I'm going to place this over the molar mass of the ammonia, 17.04. Again, 14.01 plus 3 times 1.01. So I have that. I'm going to take and square both sides. So if I have that, that will equal 5.09, equaling the molar mass of the unknown, divided by the molar mass of the ammonia. So I can multiply both sides, 5.09 times the 17.04, and that will give me 86.68 grams per mole. Okay. Now, with significant figures, I could round that to 86.7. I'll go ahead and do that real quick to be proper. Now, let me go through this and just try to answer this in one other way. So, just for instance, if you wanted to do it the other type of way where you had the 37.2 centimeters versus the 83.9 centimeters, again, this one was relating to the unknown versus the velocity of the ammonia. So when I would set that up in my equation, now notice I'd have 1 divided by the 2.26, which would be giving me a decimal of 0.442. So because I now have the velocity of the ammonia in the numerator, or in the denominator, I would need the molar mass for ammonia in the numerator and the molar mass of the unknown in the denominator. So when I would take that and I would square it, 0.442 squared, that would be 0.196, and that would be equal to the molar mass of the ammonia, which we know is 17.04 over x. So I could again multiply both sides by x, and then that would give me 0.196x equals 17.04. Divide both sides by 0.196. And if you do 17.04 divided by 0.196, you end up with the same approximation of 86.9 in this case. So again, just a little bit of the rounding issues that we would have, but somewhere very close in proximity, 86.9, 86.7. So you can get the same answer using the other flipping your numbers around, but again, it's just not quite as easy to get your numbers in the correct spots. So, and just feeling confident about your answer. So that wraps up this last video here for this unit. We'll spend a couple days going and reviewing, and then we'll be ready for your test in a couple days. So come to class with questions tomorrow. Have a good evening.